Today we're going to be talking about roof-mounted solar panels subject to wind loads. Now this one is actually an add-on to a previous seminar I've done. Let's jump to the Danny Pig YouTube channel, and you'll see within the playlist, or now course list, for CPD webinars for structural engineers, we have webinar number 6, which is about wind analysis, to NZS 1170.2. So once you've gone through that, you can add on to this one too. And while you're there, don't forget to subscribe to the channel, hit the like button, and share it with your friends. So back to today, and we're going to be using ASNZS. That's our New Zealand code for wind, 1170 part 2, and this is the 2021 edition. It's been out for a few years now, but still not yet endorsed by the New Zealand Building Code. It has a little bit more to say about roof-mounted solar panels, and so we need to take them into account when we're designing our buildings, and they're becoming more and more common. Now, the best way to put them is put them parallel, mount them parallel to the roof, and they'll have less impact on your building. If you put them in at an angle, you're likely to increase the load significantly on the mount and on the building itself. But Appendix B covers this situation. So these are panels mounted parallel to inclined roofs. And table B12 gives you the aerodynamic shape factors that you'll need to calculate the net wind pressures acting normal to the panels. So the change of wind pressure is dependent on which direction the wind is blowing. And it divides it up into an upwind end and an upwind central downwind end. And what does that mean? Well, if we click over here, we'll have also the diagrams from the code which show the differences. What do they mean by an upwind end and a downwind end? So if you've only got solar panels on one part of your roof, then you can pick that section. It's dividing your roof up into 3, basically. And similarly, if the wind is blowing in the other direction, the across direction, where theta is 0. Similarly, if you want to know where these local winds apply to, here's my little diagram that shows a plan view of a roof, and it divides it into the local wind pressure areas, where the local wind pressure factor, KL, varies from 1.5 to 3. And so these will be in the code as RA1, RA2, RC1, and so forth. And they come back in mind. So let's hide that for the moment, and we'll come back to our view of our calculations. So we begin with wind loading on the building, and we've entered the area reduction factor and the porous cladding factor both as 1. Our combination factors are 1 for internal and 0.9 for external pressures. We've got a range of local pressure factors varying from 1 to 3. So in this case, I've just put in an array, a one-dimensional matrix, if you like, which will allow you to calculate a range of values associated with each of those pressure values. Our design wind speed is entered, and in this case it's 47.2, and that gives you a dynamic wind pressure of 1.34 kPa. On our project, the roof height is 4, depth is 15, length is 26, and our roof pitch is 7 degrees. That translates into these H over Ds and H over Bs. We also derive our A factor, which is important to know when you're calculating the areas of the local wind pressure. In our case, the A is 3 meters. Looking at the roof beneath the panel, we have our usual factors taken from table 5.1, and so our roof pressure coefficients are downwards 0.2 and upwards minus 0.9, internal with a maximum of 0 and a minimum of -0.3. So from that we get our maximum wind pressures as 0.64 and our maximum wind uplifts or suctions range from -1.08 up to 3.25 when we take into account the various values for the KL. Now we look at the loading on the solar panel, and we've taken them from the table above, and so we have various values depending on whether it's an upwind or downwind end or it's central and so on. And for simplicity, we just take the maximum that we're going to be using, so we can plonk our solar panels anywhere on the roof. So the maximum positive pressure is going to be a 0.8 factor, and our wind uplift is going to be a maximum of a -1.7. So in this case, our maximum wind pressure is 1.069 kPa, and our wind suction is -2.27. So that can be significantly higher than the standard wind on your roof. Now, the little trick you need to know that suction on the solar panel puts pressure on the roof beneath it, and wind pressure on the panel puts suction on the roof beneath it. And you've got to think about it as here you have a plane and a gap on top of your roof. It's effectively like placing a wing on top of your roof. So say that again. Suction on the solar panel puts pressure on the roof beneath it, and wind pressure on the panel puts suction on the roof. So the net loading on the roof is you've got to combine the two. And depending on your local pressure factors, you can go from an upward to a downward, but your downward is counteracted by your suction. So even if you think you're doing a downward load, your uplift is actually bigger. So that's the wind pressure on the roof. What about the weight? Well, normally solar panels are relatively light, although you've got to check with some lightweight framed buildings that have been designed to the limit. So usually the lightweight steel frame sheds have been designed to the absolute limit, and there's no spare capacity in them. So it is worth checking the extra weight you're putting on and any extra equipment you're putting on the roof. But typically a panel of 1.7 by 1.1 would be around the 22 kilogram mark. It's not huge, but it's not insignificant. And so the downward is works out as 0.115 kPa if you spread it out as an area load. And if you look at the fixings, we've got a wind upload for maximum of a 4.249. Because we've got 4 fixing, the uplift on each fixing underneath the solar panel is -1.06 kilonewtons. We've got a fixing capacity, which is calculated separately at 1.7, so our utilization is at 62%. And that's it. Nice and straightforward. I'll see you in the next one.